In this section of 13.5, we're looking at implicit partial differentiation. Suppose that x and y are related by the equation capital F of xy equals 0, where it is assumed that y equals f of x is a differentiable function. To find dy dx, use the chain rule. Now here we're saying we have a function with x's and y's, and if we can set that whole thing equals to 0, let's call this w. So if you consider the function w equals capital F of xy, where y is a function of x, you can apply the chain rule for partial derivatives. Since w is a function of x and y, we could say the w dx is the partial derivative of that capital F with respect to x times the derivative of x with respect to x, plus the partial derivative of this capital F with respect to y times the derivative of y with respect to x. Now, since we are saying that w is equal to this capital F of xy function equals 0, we can say that the derivative of w with respect to x is also equal to 0. And by replacing that dw dx with 0, we get this. Now, we want to rearrange the terms here using algebra to solve for dy dx. We can subtract the partial with respect to x of that capital F of xy times dx dx, subtract this from both sides, and then we're going to divide by this partial derivative of capital F with respect to y. And so we end up with dy dx when we solve this equation for dy dx, and if dx dx is 1, we get dy dx equals the opposite of the partial derivative of this capital F function with respect to x of xy divided by the partial derivative of that capital F of xy function with respect to y. Okay, this actually ends up giving us a very useful way, useful theorem, which allows us to find derivatives implicitly. You can extend this if you have capital F of xyz, a function of 3 variables equals 0, then you can find the partial derivatives with respect to x and y using this chain rule for partial derivatives. Okay, I'd like to show you this example of finding a derivative implicitly. We'll do this using the method you would have done in Calc 1 and Calc 2, using implicit differentiation, and then I'm going to show you how we can apply that theorem that we just had on the previous couple slides. Okay, here we want to find dy dx given y cubed plus y squared minus 5y minus x squared plus 4 equals 0. Now you would have done this in Calc 1 using our implicit differentiation. So you would find the derivative implicitly by working this out and solving for dy dx. You would take the derivative of y cubed, which is 3y squared, times the derivative of y with respect to x, dy dx, plus the derivative of y squared is 2y times the derivative of y with respect to x, minus the derivative of 5y, so which would be minus 5 dy dx, minus the derivative of x squared, which would be minus 2x. The derivative of 4 is 0, and we'll say that is equal to 0. The goal when solving derivatives implicitly was to eventually solve for dy dx. So in order to do that, we're going to factor out the dy dx from these terms, and we get 3y squared plus 2y minus 5. And then I'm going to move that minus 2x to the other side. And then to get dy dx, we're going to divide both sides by this 3y squared plus 2y minus 5. So then we get our dy dx, which is equal to 2x divided by 3y squared plus 2y minus 5. That's what you would do in Calculus 1 or Calculus 2. I call that the long cut. There is a shorter way. Now that you know partial derivatives, you can find the derivative of y with respect to x implicitly using that theorem. Okay, this slide is going to take you through the steps of how we can now use the partial derivatives to find this derivative implicitly. So we're given this function, and the formula, what we do is we have to define this capital F of x function. It is just writing this whole thing. We know that this whole thing is equal to 0. That's our capital F of xy function. Then by finding the partial derivative of this with respect to x, we find that that is negative 2x, and the partial derivative of this with respect to y is where you treat y as a variable and x as a constant. That derivative is 3y squared plus 2y minus 5. That partial derivative with respect to x, you treat y as a constant, and this becomes negative 2x. So those are your two partial derivatives of this capital F of xy function. Now dy dx, using that theorem from the previous slides, equals the opposite of the partial with respect to x over the partial with respect to y. So we're going to put this negative 2x in the numerator and 3y squared plus 2y minus 5 in the denominator, and the dy dx is going to be the opposite of that. So by making those substitutions, notice that we get exactly the same thing that we found using the Calc 1, Calc 2 method. 2x in the numerator over 3y squared plus 2y minus 5. And I can go back to that where we worked it out using the Calculus 1 or Calculus 2 method. Okay, so obviously, with now using these partial derivatives, it gives us a way to solve these types of problems. Here's another one. I'd like you to pause the video, try this one on your own, and then come back and check your work. You want to find dy dx if cosine x plus tangent xy plus 5 is equal to 0. Again, I'll show you the Calculus 1, Calculus 2 method before knowing those partial derivatives, how you would go about solving this for dy dx implicitly, and then I'll go ahead and show you how we can use that shortcut to find the derivative using partial derivatives. So the way we're going to solve this is to take the derivative implicitly. The derivative of cosine x is sine x, negative sine x. And then the derivative of tangent of xy is going to be secant squared of xy times the derivative of what's inside. The derivative using implicit differentiation, we're going to use the product rule. It's the first times the derivative of the second, the derivative of y being dy dx, plus the second times the derivative of the first, and the derivative of x is going to be 1. The derivative of 5 is 0, so that's going to equal 0. So here we have our first step of the implicit differentiation. I'm going to go ahead and distribute the secant squared. So we get the negative sine x plus secant squared of xy times x times dy dx plus secant squared xy times y equals 0. Now our goal here is to solve for dy dx. So I'm going to keep the secant squared xy dy dx on the left side of the equation. I'm just going to move this x out in front so it doesn't get confused with the argument there. We're going to write this as x secant squared of xy times dy dx equals. Now these other terms I'm going to move to the other side of the equal sign to get this negative sine x. When I move it over, becomes a positive sine x, and this becomes a minus secant squared of xy times our y. Now to get this dy by itself, we're going to divide both sides by x times secant squared xy. divide that both sides. So we can say our dy dx is equal to sine x minus, I'm going to bring that y out in front, y secant squared xy divided by x times secant squared of xy. Okay, that's using the calculus 1 way of solving for dy dx implicitly. Okay. In this case, I want to show you the shortcut using the partial derivatives. Dy dx, if we have this capital F of xy function, which I'll say is our cosine x plus tangent xy plus 5, that whole thing equals 0, then we can say, again, we're using capital F here, our dy dx is found by taking the opposite of the partial derivative of this with respect to x divided by the partial derivative of this with respect to y. So the opposite of the partial derivative of this with respect to x, we're going to treat x as a variable, y as a constant. The derivative of cosine x is our negative sine x. The derivative tangent xy is secant squared xy times the derivative of what's inside here, treating x as a variable, y as a constant, that's our y, divided by the partial derivative of this function with respect to y. The derivative of, with respect to y, we treat y as a variable, x as a constant. The derivative of cosine x if x is a constant is 0. The derivative of tangent xy is secant squared xy times the derivative of what's inside. We're going to treat y as a variable and x as a constant. And the derivative of 5 is 0. So notice that when you simplify this, you get the same thing as doing it using the Calc 1, Calc 2 method. So when you distribute that negative sign, we get sine x minus y times secant squared xy, all divided by x secant squared xy is your dy dx. And then again, if you go back to the previous slide, you'll see that we end up with the same result using both the calculus 1 implicit differentiation and the calculus 3 implicit differentiation by using partial derivatives. Okay. So we get the same thing.